All right, ladies and gentlemen, today we are going to finish up with one more ideal gas item, and it's something we've talked about before, and you probably could figure it out yourself, but we're going to go ahead and just make sure that we're all on the same page, and it's ideal gas polytropic problems. So here, let's do this for polytropic processes. We know that P1 V1 to the n is going to equal P2 V2 to the n, right? Because it's PV is equal to constant. Okay, PV equals to constant. So we can write this as let's do it this way. P2 over P1 is equal to V1 all over V2 all to the n. That's using the rules of exponents. That's what we can get. Okay, so now we're dealing with an ideal gas. And so we know, hey, PV is equal to mRT. Or we can write that P1 is equal to M1 R1 T1 all over V1. And P2 is equal to M2 R2 T2 all over V2. Okay, so that's what we have with the ideal gas law. And so we want to plug this description for P1 and P2 back into the original equation. And we do that, we're going to get mass 2 R2 T2 all over V2 over mass 1 R1 T1 all over V1. And that's going to equal, what do I have here, V1 over V2 to the n. Now, we're still dealing with the closed system here. Closed system, so the mass is going to be the same. And the gas is going to be the same. So these things go away here. And we're left with this. We're left with this thing. We're left with T2 all over T1 times V1 all over V2 is equal to V1 over V2 to the n. So I did a little bit of algebra there. Move things around, make sure that the numerator and denominator, just like have a little fun with some fractions. But I notice here I have V1 and V2 on both sides of the equation, and I don't like that. I like them to be all together, reconnect with each other. And so what I'm going to do is I'm going to take this side, I'm going to take it times V2 over V1. So if I take that side times V2 over V1, I take the other side times V2 over V1, which I am. See what I did there? This is more fun with exponents. V2 over V1 is the same thing as V1 over V2 inverse. So what that does is that cancels out this side. These two things cancel out. And I'm ended up here with T2 over T1 is equal to, well, V1 over V2 to the, what do you do here with you have exponents? N minus 1. Okay, and we know this works for polytropic processes. We know this works. And similarly, gosh, man, I really need to record these things before way late at night, don't I? Similarly, I probably, let's be honest, I'm not going to say that word right at 6 o'clock in the day, in the afternoon, right when I wake up. My tongue just doesn't work properly. Watermelon cantaloupe. Okay, similarly, we could do the same thing with pressures, and we're going to get this relationship that T2 over T1 is going to equal V1 over V2 to the n minus 1, which would also equal P2 all over P1 to the n minus 1 all over n. And so you need to know something. These equations right here, which are on your equation sheet, only work for ideal gases. They only work for polytropic situations. So if you're dealing with something that's ideal gas and polytropic, there you go. You can use these to help you set states. Now the other thing that we can do here is we know that that work equals the integral of PdV, right? So let's just say that we're dealing with constant pressure situations, because we have to say that PV is equal to mRT. I think we already did this. This would be equal to pressure times V2 minus V1. We go from 1 to 2. And our pressure here we could rewrite as, we could do a lot of things. We write our volumes here. We could write this as pressure times M2R2T2 all over P2 minus M1R1T1 all over P1. And because we're saying it's constant pressure, what happens here is this pressure cancels out, and this mass and gas constant are constant, so it comes over here, and you can rewrite this as M R times T2 minus T1. Okay, that's one thing we could do. Let's say now let's say our n value is equal to 1. What was our equation? We said PV is equal to, or sorry, P1 V1 natural log of V2 all over V1. Well, PV equals MRT, right? So we could write this as MRT times natural log of V2 over V1. Or we could go up here and say, well, V2 is equal to M2R2T2 all over P2. And V1 is M1R1T1 all over P1. And so if we made this substitution here, well, we know again that our masses are constant. And we know our gases are constant. But let's figure out something here about our temperatures. Because if n is equal to 1, what do we have? We have that PV is equal to constant, right? PV is equal, that's what n is equal to 1 means, because there's a 1 here. PV equals constant. That means the constant is going to be equal to MRT. So if PV is equal to constant, that means that the mass times R times T must be constant. That means that our temperature is constant. Okay, this is very important. Here we go. We're going to put this, go here and get this one, and we're going to get the magical rainbow star. Because n equals to 1 means you have an isothermal process. Okay, very important. If they say it's a polytropic process that's isothermal, now you know n is equal to 1. You know that. You know that. And I put it into this rainbow box so that you will never forget it ever in your life. You'll wake up in the dead of night and they'll say, I shake you, because I'll come to your house, I'll shake you, and I'll say, it's a polytropic process. Ideal gas. Isothermal. What is the n value? You'll say 1. 1. Get the hell out of here. What are you doing in my house? And I'm here just because of my love of thermal. It's nothing creepy. Nothing creepy at all about me being there. Nothing at all. I have to entertain myself, folks. I really do. It's late. I'm teaching this class to people that I love, that I never see, and you have to go with it. I have some better stuff later after I get done this. I have some really good stuff coming up. Okay, so this is ideal gas and polytropic. Okay, last thing. What happens if n is not equal to 0 or 1? Okay, n equals 0 means it's constant pressure. 1 means it's isothermal. We have that work is equal to P2V2 minus P1V1 all over 1 minus n. Well, look there, P2V2. We can write this as M2R2T2 minus M1R1T1 all over 1 minus n by substituting the ideal gas law. And because our mass in R is going to be constant, our work is going to be equal to MR T2 minus T1 all over 1 minus n. You could figure these out for yourself. You don't even know this, but for ideal gases, we have 2 ways to solve the equation. Now, I want you to say that you don't have to solve them with this method. You don't have to use this equation to solve it. You can still use this one. But sometimes you may not be given a pressure or volume, and you may say, what do I do? Well, go down here And you can only use this. This is a special case. If you only use this for ideal gases. You could only use this for ideal gases. Right? That's where I'm going to end with that. I think this is pretty straightforward. I will tell you, I'm going to do a couple problems in class for the in-class version, the in-person version of this. It'll be on Friday. So if you want to see some polytropic problems for ideal gases, go ahead and log on or come to class. It's probably too late when you're watching this lecture, but look at the in-person session for today, the 25th of September, and you'll see me doing some polytropic problems. Okay, we'll end up there and we'll move on to chapter 4. Chapter 4.